The topic of acids and bases is a broad one, and one it seems that can cause some confusion. My name is Geoff Hyett, and acid-base theory is a topic that I cover in my first year lectures at the University of Leeds. A number of questions have been posted on this topic, and I'm going to try and answer them today. We should start off with some definitions. In 1923, Bronsted and Lowry devised a theory of acids based on positive hydrogen ions, which are of course protons. This theory stated that an acid was a proton donor and a base a proton acceptor. In aqueous solution chemistry, we often talk about proton or hydrogen ion concentrations. However, the free proton is unstable under such conditions and will in fact combine with a water molecule to form a hydronium ion. So for brevity, we still refer to protons or hydrogen ions, but we should bear in mind that often it is just shorthand for the actual species which is present, which is the hydronium ion. Now, the scale used to measure acid strength is of course the pH scale. The H obviously refers to hydrogen, though remarkably no one's really sure what the P stands for. What we do know is that it's simply a measure of the hydrogen ion concentration, expressed on a logarithmic scale, often referred to as being between 1 and 14 pH units. We can very simply calculate the value of the pH using the following equation. So the pH is just minus the log of the concentration of hydrogen ions. So a strong acid solution, like a 0.1 molar solution of hydrochloric acid, will have a pH of 1, while a weaker solution, say a 0.1 molar solution of ethanoic acid, will have a value of about 2.9. And of course the alkali solutions will typically have values of 8 to 14. However, values greater than 14 and less than 1 are possible. For example, a 10 molar solution of sodium hydroxide will have a pH of 15, while at the other end of the scale, a 1 molar solution of HCl will have a pH value of 0, and even negative values of pH are possible. Now, I've often stated that pure water is neutral and has a pH of 7. Now, this statement deserves some unpacking. Pure water is indeed neutral and has a pH of 7 at 25 degrees Celsius. But pH is just a measure of hydrogen ion concentration, and a value of 7 is equivalent to a concentration of 1 times 10 to the minus 7 moles per decimetre cubed. A very small but very real concentration. But if the water is pure, where do these hydrogen ions come from? Well, water can undergo a process called autoionisation, in which one water molecule can donate its proton to another, giving a hydronium ion and a hydroxide ion. Essentially, one water molecule can split into a hydroxide and a proton. Now, these are produced equally so that there's a balance of hydroxide ions and hydronium ions. And this is the true definition of a neutral solution. Of course, only a vanishingly small fraction of the molecules undergo this autoionisation, so the process is an equilibrium strongly shifted towards the unionised water. Then we can write down an expression for this equilibrium and then derive an equilibrium constant. So our water can undergo autoionisation to form the proton and the hydroxide ion. They are produced in equal quantities, so the solution remains neutral. For this equilibrium, we can generate an equilibrium constant, which is equal to the concentration of protons times by the concentration of hydroxide divided by the concentration of water. We can now make the assumption that such a small number of hydroxide and hydrogen ions are produced that the vast majority remain as water, and therefore the concentration of water remains effectively constant. So we can simplify this, moving the concentration of water here to generate a new constant, Kw. So having made the assumption that the concentration of water remains effectively constant, as such a small fraction is converted into ions, this simplifies the equation and gives us a new constant, Kw, which has a value of 1 times 10 to the minus 14 at 25 degrees Celsius. This leads nicely to my next question. Why does the pH of pure water vary with temperature? Now, not everyone is aware of this, but it does in fact occur. For example, at 50 degrees Celsius, water will have a pH value of 6.6. But remember, this is just a measure of the concentration of protons, which has increased. But so also is the concentration of hydroxide ions. All that has happened is the equilibrium position has changed in the autoionization process, so that it's shifted slightly more towards the products. If we apply Le Chatelier's principle, this means the autoionization process must be endothermic, so that when the temperature is increased, the equilibrium responds by favouring the forward endothermic reaction. Despite the pH reduction, the solution is still neutral, as the hydroxide ions are produced simultaneously as the protons. It is just the value of Kw that is changing. Now, having stated all this, it should be noted that even if I were to draw off a beaker of pure water at 273 Kelvin at 25 degrees Celsius and leave it sitting out on a table, it will not have a pH of 7. It will actually absorb carbon dioxide from the atmosphere, which is weakly acidic, and under equilibrium conditions will bring the pH down to a value of about 6, which is why it's extremely rare ever to be able to measure a sample of so-called pure water, even at 25 degrees Celsius, and get a value of 7 for the pH, unless of course you carried that experiment under an inert atmosphere. The final question is about weak and strong acids. What are they, and how do we determine their strength? Well, to answer this, we must remember that an acid is a proton donor, and that all reactions can be considered as an equilibrium. For an acid, the equilibrium we must consider is the loss of a proton, to give what we term its conjugate base and a proton. Let's consider this example for hydrochloric acid. Assuming this reaction is an equilibrium, we generate a proton and a chloride ion, which we term the conjugate base. More generally, we can write this as HA, representing any acid molecule in equilibrium with a proton, and its conjugate base. In simple terms, what we call a strong acid is one for which the equilibrium lies strongly to the right, so much so that we consider it to have undergone complete deprotonation, every molecule having given up its proton to form a hydronium ion. A weak acid, in contrast, does not completely deprotonate, but has a more balanced equilibrium point, where some of the molecules have given up their protons and some have not, so both HA and A- are present in the solution. We can quantify this by considering the equilibrium constant for the reaction and derive what is known as the acidity constant. So we can take this equilibrium and derive the equilibrium constant. Which is equal to the concentration of the protons multiplied by the concentration of the conjugate base divided by the concentration of the unionized acid molecule. For a strong acid, where complete deprotonation has occurred, this will have a value greater than 1, often much, much greater than 1, as the concentration of ionized species is much greater than the concentration of the unionized acid molecule. For a weak acid, where the protonated and deprotonated forms of the acid molecule are both present, this value will be less than 1. However, the range of Ka values is extremely large, so they're often reported on a logarithmic scale, the pKa scale, which is analogous to the pH scale, such that pKa is equal to the log base 10 of the Ka value. On this convenient pKa scale, any acid with a value below 0 is a strong acid, and anything above is a weak acid. So compounds like HCl, H2SO4 and HNO3 have negative values and are strong acids, while weak acids like ethanoic acid and phenol have pKa values greater than 0. The question as to why some compounds are more acidic than others is a bit more complex. Unfortunately, there's no one simple answer, as a number of factors are in play, such as the strength of the HA bond and the stability and solubility of the conjugate base. If we consider a simple example, however, of nitric acid, ethanoic acid and methanol, these have pKa values of -1.3, 4.76 and 15.5, a strong acid, a weak acid and an essentially neutral species. So nitric acid, HNO3, ethanoic acid, and methanol. So essentially a strong acid, a weak acid and a neutral species. All three have their proton attached to an OH bond, which will be of similar strength. So the principal difference will lie in the stability of the conjugate base. Nitric acid will produce a nitrate ion, and here the negative charge can be stabilised by resonance, essentially spreading the charge out across all three oxygen atoms. The ion itself is also reasonably small and soluble. In contrast, the ethanoate ion, the conjugate base of ethanoic acid, can only resonate across two oxygen atoms, and the larger ion is also less soluble. In the case of methanol, there's almost no resonance stability, so almost no deprotonation occurs. If you'd like to know more about this, I'd advise you to speak to your chemistry A-level teacher. Finally, I want to consider how we can calculate the pH of an acid solution. For a strong acid, this is a relatively simple process. We make the assumption that all of the molecules deprotonate, so that the hydronium ion concentration is equal to that of the acid. The pH formula is then used to determine a pH value. So for a 0.1 molar solution of HCl, we get a pH value of 1. For a weak acid, the situation is a little more complex because we have to consider that only a fraction of the molecules will deprotonate, with the exact amount depending upon the value of Ka, the acidity constant. The situation for a weak acid, unfortunately, is a little more complex. We need to consider the acidity equilibrium expression. So if we recall, our acid is in equilibrium with the protons and the conjugate base. A minus the conjugate base, and there are our protons. We derive the expression for the acidity constant as equal to the concentration of the protons multiplied by the concentration of conjugate base divided by the concentration of the original acid. If we have some solution, say 0.1 molar solution of ethanoic acid, we know the original concentration of the acid, but we don't know the value at equilibrium. So we need to consider what the values at equilibrium will be. So these three species at equilibrium, the acid molecule will have shifted to a certain extent into protons and conjugate base. So we'll have a certain amount of protons available. We'll call that value H for hydrogen. Now for every proton generated, we'll also generate a conjugate base. So the concentration of conjugate base must equal the conjugate concentration of protons. So we can use the same term, H. Finally, our concentration of acid species, well, that is going to be reduced by amount equal to the concentration of protons, because for every proton produced, we've lost a molecule of acid. So that's going to be the initial concentration, which we can term Ca, minus H, the amount that's being converted into protons. So we can put these values for the proton, the conjugate base, and the acid molecule into the acidity constant. The value for the concentration of protons and conjugate base are both equal to H, so this top line becomes H squared. The value for our concentration of acid molecule is Ca minus H. Now, if you wanted to solve this exactly, it is possible to rearrange this so you get it in the form of the quadratic expression. and that would allow you to calculate exactly the concentration of H, the concentration of protons we need to calculate the pH. However, because this is a weak acid situation, we can make an assumption. As so few of the acid molecules are going to be converted, as it is a weak acid, we assume that this value for the original concentration minus H is essentially unchanged. So this we can simplify to the initial concentration. We then have just a quite simple rearrangement so that H squared is equal to the initial concentration of the acid times by the acidity constant, and that gives us H equals the square root of the initial concentration and the acidity constant. H here is the concentration of protons, so we can put that value into the pH equation, and it will give us the value of pH for a weak acid. So now we've learned something about acids and bases, about the nature of the pH scale, and also how we can calculate the pH values for both a strong acid and, with a little bit of mathematics, for a weak acid.